So how can I find out if there is perhaps a better combination of my three parameters that I did not hit yet? Well, first of all, another nice feature here to show. Now I have several charts open with my results from the sensitivity study. So I can easily close all charts here when I'm in a chart. And they are removed step by step. Okay, so I have my sensitivity study here. Well, 3 dimensions are hard to look at, so there are other options to see my results. I would like to create a report, and I would like to have this in Excel because this allows me to easily work with a report. So I go here to the MS Excel report viewer, go back to my analysis and report the results. And now an Excel table opens where all my data points are collected. And soon an Excel table should open showing the results of this sensitivity study. So now here we have my Excel table open. And I would like to order my results. So I have to remove some points here. And now I create a table which I can work with, which is here in format as table, and the table has headlines. And now I have my table ready and I can order it by the highest methane concentration, which is 96.26% of methane. And here I can find out I reach this when I use as temperature 1 degree of Celsius, as pressure 48 bar, and 200 cubic meters of water flow. I have quite large steps here to the next size of water flow, so 50 cubic meters more. So perhaps there is a result hidden in between, which gives me higher methane concentrations than 96.26%. But finding out this with a combination of 3 parameters is a challenge. So I want to show you another tool that we have here, which is the optimization. So we want to set up an optimization, a calculation that maximizes or minimizes an objective function. And the objective function in this case should be the methane concentration in the clean biogas stream. So we create a new optimization, give it a name. So the max methane. And now we have to define the objective function. There are several nice options in CHEMCAD, but here we use the simplest one. So we just want to optimize, maximize, or minimize a single stream or unit up variable. And yeah, this is the maximum of methane concentration in stream number 3. We would like to maximize the component mole fraction of my component methane. We want to maximize, and I want to use the simultaneous modular sequential quadratic programming algorithm. The independent variables that we have are our 3 parameters. So we have for stream number 1, the total standard liquid vol rate. We started with a value of 150. And this screen, we still have to select the units. So here we are using the liquid volume rate. And this is the flow rate of water, which is min-max bound. So let's say we have a minimum of 50 cubic meters per hour and a maximum of 1,000 cubic meters per hour. Then the next variable is are our parameters in the flash unit op. So the parameter 1, which is the temperature. And let's give it an initial value of 5, but this variable is also constrained. So the minimum should be 1 degree Celsius. The maximum, let's go up to 20 degrees Celsius. And we see we have space for more variables. So we can go to page 2 now of our variables. And we have in equipment 1, the parameter 2, which is the pressure. So we select here the pressure. This is our P initial value. Let's start with 10 again. And we have min-max, so minimum should be 1 bar, maximum perhaps up to 100 bar. So now we specified our 3 variables, and CHEMCAD, or the CHEMCAD SQP algorithm, will change them for us in order to find the maximum methane concentration in stream 3. So CHEMCAD NXT is working on multiple cores, so you might know that the optimization highly depends on the initial points where we start our optimization, because it commonly finds only local optima of the objective function. So here we give it a print level of 4, which gives us more information on the results. And we see here, this is the default setting. The calculation starts 32 times in order to get a kind of globalization. We can try with more points because there might be several local optima. Well, let's leave it for this for the moment. And our optimization problem is specified, and we can run the optimization. And we can see, well, CHEMCAD found a better optimum than what we've seen in the sensitivity study. Also see it was quite fast to converge the 32 different initial points, and the final concentration of methane that we reach is 96.28%. We can accept this, which gives us the results directly into our flow sheet. And now if we run our flow sheet, we will find this solution here. 96.285 is the maximum concentration that was found by the optimizer. So still we cannot reach our 98%, but we already know that, well, higher we can hardly get with our methane concentration.